Hello everyone and welcome to this new lesson of rigid body simulation. Today I'm going to try and explain some really simple concepts of numerical integration and putting the equations of motions in place to better simulate physics. So firstly, how can we simulate physics? Well, the point is you need to find a differential equation that the system satisfies and then solve it, by integration or by other methods. Now, this comes from Newton's second law. Knowing that the mass is a constant, we know that the mass of an object times its acceleration is equal to the sum of forces applied on it. Now, this is a differential equation. Firstly, we need to find how to solve differential equations on a computer. Most of the time, solving differential equations analytically is quite hard. Maybe it's impossible. Most of the time, it's impossible. And that's why we, as humans, develop some methods to solve these differential equations numerically, basically. So yeah, the type of equations that we're gonna stumble on in these rigid body simulation systems is this kind, is y2 point, which is the second derivative with respect to time, is equal to the function of parameters t, y, and y points. Now, this one second order differential equation can be brought and simplified to a system of two first order differential equations. Y point is equal to u and u point is equal to that functions of t, y, and u. Now, let's take an example and see how to solve this. So we take an interval. We cannot solve differential equations numerically on an infinite interval. We need to specify an interval and then solve on it. So we specify an interval of 5, and then we take a subdivision number. I will take 100,000 subdivisions, which is really sometimes it's enough. This is really enough to, for my purposes, see how the system evolves. I mean, of course, a bigger value for n means higher accuracy, precision, etc. Other applications, maybe I don't know, industry or something. But yeah, I mean industry, they wouldn't use this method precisely. But yeah, it's a good first step. And we take dt as the interval divided by the number of time steps. So this is the time step. Now this is our interval, this is dt. Maybe I should zoom in a little bit. So this is dt, 2 dt, 3 dt, etc. And so int, this is the interval. We start from 0. And given initial values and the differential equation, we should be able to solve it numerically. Now this is the Euler method. Now this is the differential equation that we're going to try and solve. y2 points is equal to sine of y. This is usually found in the simple pendulum system, where this is theta 2 points equal to some constant times sine of theta. If you did some elementary physics in high school, whatnot, you will encounter this equation and you will understand that it's impossible, maybe not impossible in this case, but really hard to solve it analytically. And the way to do it in high school is just simplify sine of y for small values of y. This is approximately equal to y. And that is really not our purpose. We want to solve on any kind of y values, but of course with higher n we get better accuracy. So we need to find some initial conditions. Y of 0 is equal to 1. Of course, these are given, or you choose them for your system. Y of 0 is equal to 1, and y point of 0, which is y points are going to take y point is equal to u. And y point of 0 is equal to u, 0 is equal to 5. These are just arbitrary values that I took. So we know that the derivative is the limit as dt tends to 0 of y of t plus dt minus y of t divided by dt. That's the definition of a derivative. So what should we take? Well, we have dt small enough, there's some physicist stuff. It's not really some mathematics, it's just some physical approximations to do the numerical solution. Of course, there is no continuum for a PC, it's just discrete values. So yeah, so yt plus dt minus yt dt is equal to u of t. So if you take t is equal to 0 for the first time step, and you just take these terms to the other side, you find out that y dt is equal to u of 0 dt plus uy of 0, and you know u of 0 is just 5, dt is just 5 over 100,000, and y of 0 is just 1. So you know the value of y dt. Now you know the value of y dt, and you want to evaluate u of dt. So it's sine of y of 0, which you just calculated. No, it's just the initial condition sine times dt plus u of 0, and you know u of 0. Now you just calculated y of dt and u of dt. Now the next step, you calculate y of 2 dt, and then u of 2 dt, and then y of 3 dt, etc. And then you find a bunch of points, and then you can do the interpolation, maybe some kind of sorry, it should be like 5 or something. Yeah, and then you can do your interpolation or something. This is called the Euler method. You know, the way you approximate derivatives in that way. This is called the Euler method. Of course, there are other methods. I really don't want to edit this video. I don't have the time, so I'm just gonna keep the. I apologize for the mistakes. And there are some other methods like the Runge-Kutafor. They are more precise, but I really don't want to get into that. It's a long sorry, just go and type Runge-Kutafor or RK4 on Wikipedia. Now we know at this stage how to solve a differential equation, or maybe a system of differential equations on a PC. This is the basic idea, basically. Now we want to find the differential equation that a system satisfies. Well, let's just take a particle in the void, and on which we apply the gravitational field. Well, m, you know, the mass of the particle, times the second derivative of this vector, you know, the acceleration, is just minus mg, where g is this vector. Now let's just take OM0 is equal to 5, 3, 4, and the initial velocity is 1, 0. So basically the particle is just gonna be here, and then we'll just go up and then go down, and you can solve this differential equation. It's not really that hard. You can solve it analytically, it's really easy, and you can solve it numerically. Now, for a system of particles, M1, M2, M3, M4, M5, and maybe Mn, in a more general case, we have the Newton's second law applied for each one of them. So it'll give you mi times the second derivative of OMI is equal to minus mij, where I it's between 1 and 5. Now we can do the same thing, but you see, as we have here, OM is just a vector with 3 components. We can take a bigger vector, the state vector, this S, and it's a function of time, and it will contain a lot more components than OM. Basically, it would contain, for example, here 15 elements, actually 5 elements, within each element is 3 elements, so it's basically 15 elements, so it's a vector. And if we define this matrix M as being equal to M1 times the identity matrix 3, M2 on the diagonal, etc., where I3 is basically the identity matrix of size 3 by 3. And if we define J to be equal to J 5 times, and J is still by definition 0, 0, minus 9.81, you know, the acceleration, etc., we get this differential equation, and it's a matrix one. So it's the matrix M, S2 points is equal to matrix MJ. And of course, this M is inversible, since there are no zero masses here. We're not working with photons or whatnot. They're just classical simple mechanics. And yeah, I will just give you a simple system of differential equation that you should solve. Now, of course, initial values S of 0 and S point of 0 is just full of the initial values for each one of them. Okay, so this is for a simple case and a system of simple cases. Now, the forces, well, usually this system will look something like this: the mass times the second derivative of the state vector, which is basically a concatenation of many state vectors, OM1, OM2, etc., is equal to a function of time and states vector velocity. So basically the first time derivatives. These forces can be something like p is equal to mg. This is just a constant. It's the same everywhere. It might be a force of a spring, a spring going from point A and applied on point M. It would look something like this with characteristic K and L0. It might be friction. That's why you can have S0 in this S point in this function. Friction will be something like this, F minus alpha S point something whatnot. You can have gravitational fields with might look something like this, minus S over S, the magnitude to the power 3, and then times a constant. There are a lot of forces, gravitational, electric, magnetic, etc. But it's basically the same principle. Now, the hard type of these forces that we don't really know how to compute, this is easy, this is easy, this is easy. It's all functions of S, etc. And we know them. This is Hooke's law, whatever. There is Coulomb's law and Newton's gravitational law for, the force laws that I just wrote. But the hard ones are constraint forces. Let's take an example. Let's say we have a simple pendulum, and there is, our point M attached with a bar to the point M, O, and we have a constraint that is that OM should be always a constant distance. Now, if we want to do it the simple way, M times the second derivative of the states vector is equal to its weight, B, plus T, which is the force that is applied by O on M to satisfy this constraint. Now T, we don't really have a formula for it, and to find it, well, as we did in high school, you can take this as ER and this as E theta, and then you see that T has no components on E theta, and you just simplify the equations. You find out that theta 2 points is equal to K sine theta with K constant, and then you integrate it. As I said, you cannot do it analytically, you do it maybe numerically or by approximation, and then you find T is equal to a function of theta and theta point. Well, this only works in really simple cases, and we are trying to generalize here, so into the bin. Now we need to find a method to do this in more general cases, introducing the Jacobian. Okay, so we come back to the origin. Why is this force even existing? Well, it's there to satisfy a constraint. Our constraint in this case is x squared plus y squared plus z squared is equal to a constant. Of course, x squared plus y squared plus z squared is the length of this bar squared. Since the length is a constant, then its square is a constant. I don't want really to do the square root because, the derivative of square root, it will just give you 1, 2 over square root of x, and maybe something here, not x. But anyways, I don't want to deal with 0 in the denominator. I just don't want to deal with that. So we just go the easy way with the square. Now this is equal to constant, which means its first derivative with respect to time is equal to 0. Now c point is equal to 0, and c point is by definition the partial derivative of c with respect to time. Now this, well, we can write it as this form. It's dc over dom, dom over dt. Now wait a minute. We know how to differentiate a scalar function with respect to a parameter, and we know how to differentiate a vector function with respect to a parameter. We just take the derivatives of its components. But what is the derivative of a scalar function? And after that, I will show you that this c will become a column vector. What is the derivative of a vector with respect to a vector? Well, it's really called the Jacobian. It's not really that hard. I mean, it's a definition in math. It's a definition in math, just like any other. If you have a scalar function, a vector function f of x1, x2, and xn parameters, written as this column vector f1, their components, then the Jacobian of this function is this one, the partial derivative of f1 with respect to x1. And then you go all the way until the partial derivative of f1 with respect to xn, and then you go the other way, fb x1 and then fb xn. That's the definition of the Jacobian. And indeed, if you multiply this function by the first time derivatives of each component, you will actually obtain f point of x1, x2 and xn. Okay. This is just a simple math definition. You can just visit their its definition page on Wikipedia, and you'll understand it's just a definition.